Hello everyone, and welcome to today's webinar with IHI TerraSun, where we'll be discussing what experts think you should know about UL9540 Codes and Standards for battery storage. I'm Andy Colthorpe, editor of Energy Storage News at Solar Media. I expect it's not at all surprising to anyone watching this webinar or visiting the Energy Storage News website that the safe installation and use of energy storage systems is pretty important. Codes and standards define much of the modern world around us, and the transition to clean energy is no different. Energy storage as an industry is often compared to solar PV, in that both are relative newcomers to the energy sector, rapidly gaining traction and establishing growing scales of manufacturing and deployment. While in some ways that comparison between PV and energy storage falls short when we get into the details, it certainly holds true when we consider the way solar PV gradually became a bankable technology or set of technologies that investors could become comfortable with. Now, energy storage is at an earlier stage of that journey into mainstream acceptance, and much of the work being done by our speakers in today's webinar, together with a broad range of stakeholders in the industry, will likely have a big impact on the growth of energy storage for years to come. Codes and standards play a vital role in that journey to bankability, and again, we're in good company with today's expert speakers to help guide us through the fascinating but often complex set of considerations that make up the industry. Even if in a perfect world there were no such thing as money and bankability wasn't an issue, without public confidence, no industry and certainly no energy technology could establish itself as a vital cog in the global market. And again, it's sometimes easy from an industry bubble perspective to forget that most people aren't really up to speed yet with how batteries best need to be taken care of. Just this week, a new initiative has begun to establish standards for micromobility after a spate of fires involving scooters and e-bikes in New York. The risks can be managed safely, but they will always need to be paid attention to. And it's important to bear in mind that standards are an evolving piece just as much as the technologies they're applied to are evolving and being innovated in. Today, we'll be hearing about some of the latest changes and updates and how they could impact your business. So I'm very happy to have joining us today on the webinar Larry Kane, who is VP of Engineering and Projects at IHI TerraSun. TerraSun provides integration, software and services for large-scale energy storage projects, and TerraSun is a subsidiary of the multi-billion-dollar energy conglomerate IHI Corporation. It's also important to note that Larry serves as a member of the UL9540 Standards Technical Panel. Also with us are Dr. Carrie Kaplan and Dr. Mark Kellenberger from DNV. Mark is a senior energy storage safety engineer, and Carrie is a lithium-ion battery expert and the energy storage safety team lead at DNV. And last but by no means least is Steve Douglas, who is Senior Technical Code Specialist at QPS Evaluation Services, Inc. And Steve, like Larry, is also a member of the Standards Technical Panel for UL9540. Of course, interaction with you, the audience, is really important to us, and we welcome and encourage you to submit your questions for the speakers ahead of the Q&A session at the end of that panel, the end of our presentations. Also, just quickly to note that we won't be able to tackle all of the questions. We're expecting a lot of them, but our experts will be more than happy to continue conversations with you offline after the session. And lastly, today's session will be recorded, and all registrants sent a link to the recording as well as presentation slides. So with that final bit of housekeeping out of the way, I'd like to hand over to our first speaker, Larry Kane. Larry, the floor is yours.
Thank you, Andy. Appreciate that introduction. As mentioned, I'm Larry Kane with IHI TerraSun Solutions. I've been here for 5 years, focusing specifically on the energy storage sector and batteries in particular. But prior to that, I do have 18 years of experience in the nuclear power sector, either in the Navy or in the commercial power plant design business. Today's presentation is to talk through UL9540, what it is, why it's important. As an integrator of battery systems, what we have to do to make sure that any project is successful, how to document that your system will be meeting all of the codes and safety requirements, and how to interface early and frequently with your local authority having jurisdiction. So UL 9540, it is a required safety listing and a certification for energy storage systems. And the focus today will be on the battery energy storage systems. It's currently in revision 2. The first edition of the standard was issued in 2016. The way the standard is put together is there is a technical panel of right now roughly 124 members throughout the industry that make recommendations and changes to help the standard develop, evolve, and become safer for all participants. As mentioned, Steve Douglas and I are both members of that committee. Other types of members include energy storage manufacturers, various testing labs, different systems integrators, and of course, utilities across the United States. Proposals from the members are made as necessary in order to improve the standard and make changes that are seen in the industry. We do think that a possible third edition, which is going through review right now, will be issued in 2023. What UL 9540 does is it ensures that battery energy storage systems meet the major electrical safety codes for site safety and personnel safety. Those include NFPA 70, which is the National Electric Code, NFPA 855, which is the standard for the installation of stationary energy storage systems, and that one in particular has now become the nationally accepted code that local and state jurisdictions can reference. And then, of course, the International Fire Code. UL 9540 can be applied specifically to battery cabinets, or it can also be used to include the inverters and DC converters for systems that are either AC coupled or DC coupled. As an integrator, when working on projects for 9540 compliance, it's important to review all of the safety features that will allow that system to operate properly and protect life safety and land safety and personnel. So to do that, a safety analysis must be created, and within that safety analysis, you need to have a hazards mitigation analysis and failure modes effects analysis. And in follow-on slides, I'll show examples of what those look like and what goes into them. At TerraSun, when we create these documents, we follow military standard 1629 alpha for creating our failure modes effects analysis. What goes into the safety analysis is a very thorough and detailed description of the control system, its features and functions. We document all of the subcomponents of the system to ensure that they have either been tested already by a national lab or will go through testing as part of the UL 9540 field evaluation. We also must document critical failure modes and causes to be able to prove to local authorities having jurisdiction that the system will perform safely and that the systems that are designed for those safety features have been thoroughly tested. Here's an example of a control system architecture. Each portion of this system design will be thoroughly documented in the safety analysis to cover the components used, the manufacturer's make and model, failure modes, and frequency of failure to ensure that if something is critical for operation, it has been proven to operate in that capacity. The subcomponents are documented, again, to make sure that every individual item has been tested or will be tested. In this example, we see going through the fire suppression system, inverters, which typically will have their own UL listings. A good note is what you see for item 4, a unique DC disconnect on a project that in this example was tested by QPS in the field as part of the UL9540 field evaluation. And to date, TerraSun and QPS have done roughly 40 projects together with successful field evaluation and certification. The critical failure modes need to be identified by the integrator to ensure that the battery system, the associated inverters or DC converters with it, and the safety functions are evaluated in a way that thoroughly looks at each component, how it could fail, what measures are there to prevent failure, and what critical components have been designed and tested for that mitigation. We consider category 1 and category 2 failures here, which are catastrophic, that can cause serious death in this case, or critical failures that could lead to personnel injury or major property damage. The short circuit pathways and protective devices also must be looked at, considering each component in your system, be it the batteries, the inverters, if there are cooling systems needed, such as air-cooled HVAC units or chillers. Every one has to be tested and evaluated to ensure that it's not susceptible to fire or any electrical failure. Finally, a failure modes effects analysis worksheet is created that really details all the components of the system. Here is an example of just the high-level items for the battery system, the power conversion system. These are just the top level, but within each category, we will go through and document all of the various components, their severity class, and how they could fail and how that failure is mitigated. Now, we'll talk briefly on changes in the industry that we are all still working through and in ensuring that new projects meet. The biggest change recently was in 2021, September, NFPA 855 changed to now require that battery cabinets meet either NFPA 68 or NFPA 69 requirements. NFPA 68 is deflagration venting, and then NFPA 69 is explosion prevention venting. So previously, energy storage cabinets, while maybe they were required to meet these requirements, it was not specifically stated. And NFPA noticed that, and then a change was made, which is now permanent in the 2023 edition of NFPA 855. When complying with NFPA 69, a gas detection system now must be provided with 24 hours of standby power and 2 hours of power in an alarm state, whereas previously this type of backup power was not required. So this goes into the site design that both the integrator and developer need to consider for how separate and independent standby power will be provided. When meeting either NFPA 68 or 69 requirements, actual testing and or CFD analysis will be necessary to prove to a local authority having jurisdiction that your product meets the requirements. And TerraSun, we have previously worked with DNV on projects for NFPA 69 compliance, where very detailed CFD analysis of the full battery cabinet, how gas is removed from the system and how gas enters the system in a failed state is done to prove that the gas removal will keep the system safe and below the flammability and explosive limits allowed by the code. A final update to note is that with the 2023 edition of NFPA 855, smoke and fire detection systems also have to have the similar 24-hour standby power and 2 hours in alarm, and they need to be in accordance with NFPA 72. Every project really needs to be considered individually for what products will be used and how that project will function at the site. The battery manufacturers come up with new products roughly every 2 years, but it's important that as each new product comes to market, the integrator has a very detailed vetting process to go through the codes and ensure that there's compliance before starting any project. Failure to do so can result in delays to permitting and the ability to operate the site. So you have to go through and work with the developer and the authority having jurisdiction of the site to ensure that the 855 requirements, 9540 requirements, but also local codes and any individual requirements for that site are provided. And that is something that at TerraSun we really pride ourselves on, of being able to work closely with the developer, the EPC for the project, and getting early interface with the authority having jurisdiction.
Excellent.
Andy, thank you. Yeah.
Sorry, a bit of an overlap from me there. Apologies for that, Larry. That's a great overview of, what I think is, clearly a very complex topic, and we'll be hearing more from Steve, Carrie, and Mark on other aspects of it. But just before we get into their presentations, I'd just like to exercise my editorial privilege and ask you a couple of questions, Larry, if I may. And also just to note that there are a ton of great questions coming in from the audience. I don't know if you've seen that yet, Larry, but we look forward to trying to tackle at least some of those. But as we say, anything we can't tackle, IHI TerraSun and everyone on this webinar will be happy to follow that up offline. So Larry, and kind of your position as an engineering perspective on some of these really big projects that you guys are doing, especially. I'd be interested to know how integrating systems with components from different and often third-party providers can be a challenge in terms of those safety standards.
Right. So we do work with many third parties on the battery side and on the inverter and DC converter side. So it is tricky when having a more agnostic approach, but what you gain from that is you understand how all the individual components work, and you really are able to then build a system around them. One of the things at TerraSun that we do internally without any third-party support is the overall site control system is always developed by us specifically for the products that we are using in the field. And in that way, we thoroughly test everything with those vendors prior to getting to the field and making sure that we meet the code compliance and safety requirements.
Okay. And not an entirely unrelated note, I guess, but yeah, just wondering how can integrating different types of battery storage, and I guess we're sticking broadly with lithium-ion here, but different types, it could mean different configurations as well. So DC coupled versus AC coupled, hybrid resources, which might be, say, solar and battery storage versus standalone battery storage, and perhaps any other differences that you can think of, Larry. Yeah, how do those then differ in terms of what needs to be done to meet those standards at project or increasingly even at portfolio or kind of fleet level, I suppose?
Right. The different kinds of projects that we've integrated, standalone batteries, AC coupled and DC coupled with solar sites, really the focus is on the product with the battery and then the inverter. So from an overall safety perspective, as long as the products we use, the battery cabinet and the inverters, go through their individual testing. So for the batteries, you still need to ensure that UL1973 testing is already done from the battery manufacturer, and UL1741 for the inverter manufacturer. Then what it really comes down to is the control system. And again, as I mentioned, that's where TerraSun works to build that specifically for the unique project at site and to meet our customers' exact needs.
Cool, excellent. Yeah, I mean, there's probably plenty more we can delve into, but you know, we have limited time, so we'll have to shuffle along. But yeah, with that, I'd like to introduce Dr. Carrie Kaplan, Dr. Mark Kallenberger. Over to you guys.
Thanks, Andy. Good morning, everyone. Today, my colleague Mark and I will be discussing large-scale fire testing, in particular the UL9540 test standard, its intention, typical test data, and how the test can be used. We'd also like to discuss some fire suppression systems and some explosion controls. So UL9540 is a test method for evaluating thermal runaway fire propagation in battery energy storage systems. It is currently in its 4th edition, and its overall intention is to assess the hazard characteristics of a BESS that can undergo thermal runaway. If it first tests if the basic component of the battery can undergo thermal runaway, and then evaluates the fire and explosion hazard characteristics of that BESS. The test can then be used in a variety of different ways, including informing the design and safety features of the BESS, as well as setting some minimum spacing requirements for battery installations. It is important to understand here that all lithium-ion batteries currently on the market have the propensity to undergo thermal runaway, which is why testing is so important. So when is testing required? Both NFPA 855, the 2023 version, and the 2021 version of the International Fire Code, the IFC, require UL9540 testing or equivalent testing. And then the large-scale fire testing, again, is required for most installations. So it's important to note here that the UL9540 test is not a pass-fail test. Instead, there are 4 outlined levels of testing, each with their own performance criteria. So in order for a technology to end testing at a certain level, the performance criteria do need to be met. So the performance criteria are designed to answer some of these questions outlined here. At the cell level, can the cell undergo thermal runaway? Are the vent gases flammable? At the module level, is there thermal runaway, or is the thermal runaway contained by the module design? Again, are the vent gases flammable? In the unit level, does the heat generated affect the surrounding exposures? Is there an explosion hazard? Is there a fire hazard? And at the installation level, are the fire and explosion mitigations effective? So typically we do not see installation level tests because lithium ion based batteries at least don't reach this level. So before we move on, I do want to stop for a moment and talk about what thermal runaway actually is. Thermal runaway is ultimately the uncontrollable self-heating of a battery. A cell undergoing thermal runaway will have chemical reactions that produce heat that then in turn cause chemical reactions that produce heat, which causes this cycle of the self-propagation. So typical test data for a cell undergoing thermal runaway usually looks something like what is shown here. There are 2 important temperatures during any thermal runaway reaction, the cell venting temperature and the thermal runaway onset temperature. And these temperatures are described with those dashed lines that you see. It is possible to cool the battery after the cell has vented, but before thermal runaway has been reached to avoid thermal runaway, which is why these 2 temperatures are so important. So some other important data considerations for the cell level are the off-gas volume and its composition. For the module level, the level of thermal runaway propagation between cells, and the 4th edition test does require that cell-to-cell propagation. And then the flammability of that off gas is also important for the module level. And the unit level, the effect of thermal runaway on the adjacent exposures, and the exposures are defined as that of the target BESS surrounding the initial unit, the walls, any walls that are present, and then the means of egress. I'd like to now pass it to my colleague Mark to discuss some more on how we can use the test data.
Thanks, Carrie. So what can we do with all this test data we get out of the UL9540 tests? Well, as Carrie mentioned, we had some important data, including temperatures, gas compositions, and gas volumes. At the cell level, a lot of the considerations can be given to BMS monitoring and alarm considerations. So that is setting different alarm temperatures, setting different cutoff temperatures. So the BMS is meant to protect the cells from damage. So if the BMS detects any temperature or electrical anomalies outside of the normal operating conditions of the battery, it can take action to disconnect the battery to prevent cell damage and potential thermal runaway. From the cell level tests, cell vent gas composition also plays an important role in being able to evaluate the fire and explosion hazards posed by a particular system. So gas compositions and further on gas volumes from the module level tests let us run simulations to be able to evaluate the effectiveness of both explosion and fire controls within the BESS enclosures. At the module level, in the 4th edition of UL9540A, where thermal runaway propagation is required to be observed, this can give us an idea of the volume of gas that's generated within the enclosure unit. And further down the line, the unit level tests can help us evaluate minimum spacing requirements, egress paths, distance from walls and flammable materials within the container as well. So these allow us to support different fire suppression considerations to evaluate their effectiveness. And also allows us to take a look at the overall configuration of the BESS unit and how it's best laid out, including the location of fire detection and suppression equipment. So how can fire prevention be implemented in a BESS unit? So first of all, there are 2 steps here. One is detection of an anomaly event, and the second is potential suppression of that event. So the first level of fire protection is at the cell level. The cell design will dictate the difference between those venting and thermal runaway temperatures that Carrie described. Now, typically, the larger the difference in these temperatures, the more time the protection system has to act and to potentially stop a thermal runaway event. Now, traditional fire detection equipment such as smoke detectors and heat detectors are often used, but in cases where battery cells have little separation between venting and thermal runaway temperatures, these external detection methods might not be effective in detecting anomalies until it's too late to stop thermal runaway. So that's why when we're looking at the cell level data, the larger the separation distance between the venting temperature and the thermal runaway temperature typically means that the system has more leeway to act to prevent a catastrophic event. So the battery cell resistance to thermal runaway, as determined in the module level UL9540A tests, because becomes of high importance too. Because if we have thermal runaway in a cell that's able to propagate, we can have a cascading effect where multiple cells within the unit can off-gas and generate large volumes of flammable gases. So I talked a little bit about smoke and heat detectors. There's also kind of a new class of detector coming on in the lithium-ion BESS space right now, which are electrolyte vapor detection systems. And these systems look for fine particulate matter generated from the electrolyte within lithium-ion batteries and promise to offer earlier detection signals that the energy management system within the BESS can act on to prevent thermal runaway. More on the external side now, visual and audible fire alarms, often linked to monitoring and human-machine interfaces external to the enclosures, can provide information for first responders to act. Emergency stop buttons are able to manually open contactors if for some reason that isn't done automatically. And fire suppression systems within the container can involve a few different things. Commonly, we see clean agent gases being used, aerosols being used as fire suppressants, and typically what we see is that these are great for knocking down flames and for putting out non-battery fires. The issue with lithium-ion battery fires is the fact that thermal runaway can propagate through the cells, and it takes a lot of energy to be able to remove heat from the cells to be able to cool them to a level where thermal runaway will not propagate. And because of this, DNV really sees water-based systems, either as sprinklers in the container or dry risers that can be connected in an emergency situation, to really be able to cool the batteries, to be able to remove a large amount of heat from the batteries to prevent that thermal runaway propagation. Now, first responders kind of have two different methods for tackling these lithium-ion fires. One of them would be active engagement, and the other one is kind of a let it burn philosophy, where measures are taken to prevent spreading a fire to adjacent battery units. And this depends a lot on the experience that the local fire department has in working with lithium-ion fires, as well as any knowledge that they've gained from doing any trainings on these fires. And what we like to try to do, as Larry mentioned, that IHI likes to try to do, is to engage AHJs at an early stage in the development process to be able to interact with first responders and develop emergency response plans to be able to tackle battery fires and have site-specific rules to follow when engaging fires on sites. Now, when we're looking at some of this gas composition data we get out of the cell level tests from UL9540A, typically we see between about 30 and 50% hydrogen in these gas mixtures. Now, hydrogen is a very reactive gas, so it's important to have robust explosion prevention and protection systems within the container. And using this gas composition data, as well as gas volume data from the module level tests, we're able to put these into models for the battery container. Now, a lot of design work goes into designing the HVAC and cooling systems for the batteries. So we know we have a good idea of the airflow within the container in an air-cooled environment, and we're able to use this data from the cell level test to be able to see how these explosive gases move within the container and to evaluate whether constant gas concentrations in the container ever reach above the lower flammability limit, where there could be an explosion risk. So many containers employ gas detection systems to be able to detect flammable gases within the container. And based on some of these gas detection systems, we can have emergency ventilation systems that kick in to reduce the concentration of these flammable gases within the container. On the other side, explosion protection can involve deflagration venting panels. And to be able to evaluate the effectiveness and the need for these panels, we need to know how an explosion can evolve within a container and the pressures it can generate within the enclosure. So that allows us to effectively evaluate the location and the size of deflagration venting panels within the container. So overall, we're using a lot of the UL9540A test data to inform and to verify the safe design of BESS containers. Back to you, Andy.
Excellent. Thank you very much, Mark and Carrie. A couple of quick questions from me for you two experts from DNV before we move on. And yeah, as mentioned before, lots of questions from the audience, so it's always lovely to see. So maybe Carrie, if you'd like to go first with this one, and a little bit of a provocative pair of questions, I'm afraid. But yeah, is the battery safe, inverted commas, if it has gone through UL9540A testing? You know, how do you kind of really define that or look at it, I guess?
Sure, great question. So UL9540A is designed to inform on the extent of thermal runaway that a system can undergo. So this is directly linked to how safe the battery is, but the tests also inform on what safety features are also additionally needed, as Mark discussed earlier. So just because a BESS has gone through testing doesn't necessarily guarantee that it's safe. So DNV definitely recommends adhering to the latest standards and regulations, such as the NFPA 855 and the IFC 2021, to increase the safety of the system.
Cool. Okay. And yeah, I mean, one that I always like it when the questions I've got to ask kind of, echo some of the things that the audience is asking as well. So, and I guess this one was bound to come up, but there's a question here: which is safer, NMC, so nickel, manganese, cobalt, or LFP, which is lithium iron phosphate, of course. I guess you can see where we're going with this one. Maybe just a quick explanation of that, if you will, please.
Sure, we also get this question all the time. So both can go through thermal runaway. Again, any lithium-ion battery on the market today can go undergo the thermal runaway. LFP does have a higher thermal barrier in order to have that thermal runaway happen than the NMC. So it's safer in that sense. It requires more energy to start those thermal runaway reactions.
Right, cool. Okay. And Mark, from just a couple for you as well. Just wondering, kind of, are there any ways that UL9540A should not be used? And, are there perhaps some shortcomings with that, as a testing regime, I guess?
Yeah, so as Carrie said, UL9540A should not be used to determine if a battery is, quote, safe. So when UL9540A testing is happening, you have to remember that the test method used to send the battery into thermal runaway is not the sole failure method or fire risk that's associated with the BESS unit. There could be, in many times, a cell heating method is used to heat the cell to thermal runaway, but the battery could behave differently if the cell is penetrated, if there's an electrical fire within other parts of the container, if there's an HVAC system failure. These are all things that aren't considered by UL9540A. And some of the shortcomings, some of the test data we get, all those gas compositions are related only to a single battery cell. So when we're trying to determine maybe some toxic hazard risks from a more engulfed entire BESS unit fire, this doesn't really inform a lot of those toxic hazards that are associated with it. Doesn't give us a full analysis of the gases. There's many plastics, electronics, paints within a full BESS enclosure that would burn in an engulfed fire scenario that aren't considered in the UL9540A gas composition tests.
Okay. I mean, I guess to some extent, we should be not necessarily kind about UL9540A, but I guess realize that it is a question of being an evolving kind of work in progress to some degree. And I think on that note, Mark, what sort of improvements or changes do you think are kind of in the works to this type of testing and certification sort of regime?
Yeah, so UL9540A, much like all the standards, are actively undergoing revisions right now. There's actually revisions out for public comment right now on UL9540A. A lot of the changes involve minor revisions and updates, clarifications. One big one that we're monitoring is revisions to definitions or how testing is performed on containerized BESS units. So we're seeing a lot of shipping style containers, large units that have battery modules slotted into them. And it's not entirely clear on what the unit level definition for these is. So there's some clarifications being proposed with UL9540A to kind of determine how these large units should be tested and what should be required of those tests.
Okay. So yeah, watch this space, I guess, metaphorically speaking, everyone. Okay, great. Thank you so much for that, Carrie and Mark. And with that, let's move on to our, I was going to say third, but I guess fourth speaker of today, Steve Douglas with QPS. Hi, Steve.
Hi, and good morning. In this session, we're going to be talking about approval, listing, and labeling of equipment in general, We'll talk about the standards specifically for energy storage systems, what is involved with the or project review, field evaluation of energy storage systems, and our involvement with the authority having jurisdiction on projects. We'll start off first with looking at the Canadian Electrical Code that has a requirement that all electrical equipment, including energy storage systems, are required to be approved. Now, approved in the Canadian Electrical Code gives two options. It's a full certification or field evaluation. Full certification would be where the certification organization reviews the product and gives the manufacturer permission to place the certification mark on the product. The field evaluation would be where a field evaluation body or inspection body would look at each individual unit and put a field evaluation label on each unit. In the National Electrical Code, in Article 110.2, it talks about approval of electrical equipment as well. In here, it goes on to talk about listing and labeling of electrical equipment for use in the United States. And listing and labeling is the terminology that's most used rather than the word approved for equipment in the US. Listing means that when a certification organization looks at a product and certifies that product, they'll be included in a list that's public. So anyone can go and look to see, yes, that product was actually reviewed and listed by the certification organization. The labeling would be done after the listing is complete, and the labeling would be done by the manufacturer in most cases that the certification organization allows the label to be put on. The certification organizations that would do this for the US, the most common title for that is a NRTL, which is a National Recognized Testing Laboratory, if you've heard that term before. So this is who would be doing this listing and labeling. Full certification marks. Now, what we have on the screen here is just a few of the many. There are many more than this, but this is just an example of some of the maybe more popular certification marks that are out there. Whether it's the CSA mark, Canadian Standards Association, QPS mark, Intertech, TUV, there's two different ones there, and UL. One thing I wanted to point out is we get questions regarding the two different types of UL marks. The one on the left is a common mark that people have seen for quite some time. The one on the right is a newer mark that actually provides a little bit more information than what they used to. And I think eventually you'll see all of the marks, what I believe anyway, will go to this type of marking. That'll say that the product is certified, and underneath the certified mark, it says safety USCA, which refers to US and Canada. It also includes the UL file number so that it makes it easier to look up on the listing what products are actually covered by that listing. The next marking that you could see is a component recognition mark. There are two out there. CSA has the component recognition mark with a small triangle at the 4 o'clock position, and UL component recognition mark is a backwards RU mark. These marks mean that the product was certified, but it's not completely certified for use. There are conditions of acceptability in most cases that would need to be met as part of the full certification or field evaluation of any of these components that are included as part of a certification or field evaluation. The standards that are used for energy storage systems, which have been mentioned before, and Larry mentioned those, which UL9540 is the main standard for energy storage systems, and that's for both US and Canada. The next is UL9540A, which which Carrie was mentioning, was talking about the thermal runaway testing for energy storage systems. UL1973 is the test standard for the batteries themselves. And then NFPA 855, as Larry mentioned, is the installation standard that's used in the US. The NFPA 855 document is not a document that is recognized by authorities having jurisdiction in Canada. In Canada, you would rely just on the rules that are in the Canadian Electrical Code in section 64. In the US, in addition to NFPA 855, you would have the requirements that are in Article 706 of the National Electrical Code. Now, when certification starts on these systems, it would start with the batteries. So it would start with UL 1973, and then it would progress to testing in UL 9540A. Once that's all finished, then we would apply UL 9540 to confirm that the overall energy storage system meets the requirements that are in UL 9540. In 9540, there is as part of the scope, it refers to figure 6.1 that tells us what is an energy storage system and what comprises of an energy storage system. The thing that's a little bit confusing, the way that the scope is in the current code or in the current standard, is that one would read this and look at this figure and may come to the conclusion that the energy storage system would need to include everything that's inside that box. Now, if you look at the picture on the left, there's a 5 megawatt hour energy storage system, and the batteries and most of the controls and protection is inside that sea container looking enclosure. There's an air conditioning on the end, and then behind it there is a conditioning unit or inverter, and then behind that is the transformer. The question that comes up is, when we look at an energy storage system, does it have to include everything that you see in the picture, or is it just part of it? And there is a note in the scope that does say that specifically for a DC coupled unit, that it could be just the batteries and either the charge controller or the controls for the batteries. It does not have to include the power conversion equipment or inverter. The next edition of UL 9540 has a scope change, and the change to the figure 6.1. This will make it clear to show that yes, in fact, you can have an energy storage system that just has the batteries and the controls for the batteries. You don't have to have the converter or the inverter as part of the overall energy storage system, which makes things a little bit easier to address and avoids the overlap of jurisdiction from authority having jurisdiction and the certification or field evaluation agency. During the review of the project for an energy storage system, when we're looking at UL 9540, we would look also and review the safety analysis that are provided, the fire risk analysis, the arc flash analysis, and the critical component safety analysis. All of those were referenced and talked about by Larry, that talked about what they are and what they do with those. But when those documents are provided as part of the overall product or project review, we would review all of those documents as part of our review for 9540. While we're doing this, we also review the single line diagram, all of the components that are involved with the energy storage system, the equipment layout. We look at clearances within the energy storage system, the cabling that's used, that it's appropriate for the application, overcurrent protection that's provided or that is needed, the temperature controls and verification that the temperature controls are working, the fire protection that would be required is looked at, and the grounding and bonding requirements that are all part of the 9540. And then of course the testing that would be required as well. Now the picture that you see there, that is a 4 megawatt hour energy storage system vessel. UL9540 also has installation, commissioning, operating, and maintenance instructions that must be included, and that's all reviewed as part of the certification or field evaluation of the energy storage system. And we would review the commissioning and decommissioning documents that are included with the installation instructions, the complete installation instruction, initial acceptance testing and procedures that are provided, ongoing inspection testing procedures are included, instructions for retrofitting system components would need to be included, instructions for providing working clearance, and this would be outside of the energy storage system. The working space and clearances within the energy storage systems are covered within the standard itself for the components within the energy storage system, and additional fire suppression and fire protection identified in UL9540A test reports. So once, as Carrie was mentioning, those tests are done, then that information is used when the analysis are done for this, and then it's included in the instruction manual. The other thing that is included in here is minimum separation distances between energy storage systems would also need to be included. The field evaluation of an energy storage system, and I think what I'll do is I'll maybe talk about the differences between certification and field evaluation. On a certification, as I mentioned earlier, the certification organization would allow the manufacturer to put the certification mark on the nameplate for the energy storage system. As part of that process, the certification organization will do audits, a minimum of 4 audits per year on the factory to verify that the energy storage systems that are being manufactured still comply with the report that was created for that specific energy storage system. Excuse me. On a field evaluation inspector would look at every energy storage system. So it isn't an audit process. We look at every single one, and the label for a field evaluation label would be applied by the field evaluation inspection body inspector that's out there. The label at the top, the blue label at the top on the left, is a field evaluation label typical for US applications. In addition to that label, the label on the right would tell the authority having jurisdiction what standards were used as part of the field evaluation. So, and specifically what year was used as well, because that's very important in some applications. The blue label at the bottom on the left is the SPE 1000 field evaluation label for any electrical product, including energy storage systems, for use in Canada. The label on the right at the bottom also includes the year of the code and the year of the standard that was used for that energy storage system. So it just avoids additional questions and speeds up the process on site when the authority having jurisdiction inspector attends the site and looks at the installation. The other thing that we look for as well, and it's not just for field evaluation, but for certification, is that an emergency site contact information needs to be included on these units when they go out. So if there is a problem, the site knows who to contact for this information. And that's all I had. Andy, thank you.
That's brilliant. Thank you so much, Steve. And yeah, a lot of questions in from the audience regarding that kind of field evaluation versus factory. But So I'm really glad that you were able to address a lot of those questions within your presentation. But just a couple of quick questions from me before we hand over to the audience. And yeah, as I say, lots of questions from them. But you mentioned, of course, that NFPA 855, so National Fire Protection Association's key guidance, applies in the US for authorities having jurisdiction, but not in Canada. And I think the Electrical Codes and Standards for Energy Storage Systems in the UK, where I'm from, aren't really set as such as yet. And so a lot of folks are leaning on what's being done, I guess, in North America. But yeah, just wondering if you have any comment with regards to that and kind of how you see that perhaps being adopted outside of the US and kind of what it really means for those AHJs, really, I guess.
Okay, thank you. The NFP 855, when it was produced intentionally or intended for use for the United States. And there wasn't content for, if we look at Canada, for example, there wasn't content put in to address differences between the US and Canada as far as codes and standards are concerned. So as an example, just as maybe a simple example, the definition of a dwelling unit is different in the US than it is in Canada. Those sorts of things would need to be addressed in the NFP 855 document. I think that it would be a good thing if that happened, if we could get 855 modified to include other countries like Canada. But until that happens, I think you'll have a hard time getting it adopted in other countries, unless it's going to include the national deviations for that country. Thank you.
Right, absolutely. Thanks, Steve. And also, you mentioned in your presentation that figure 6.1 in UL9540 is not really clear on what comprises an energy storage system. And I kind of understand that there is some updating being done to that, as you mentioned. But what limitations could that lack of clarity perhaps put on the ability to meet standards? And how will the update kind of really address that?
Yeah, thank you. The question would come in under the jurisdiction of the wiring. So if I went back a couple slides and looked at a picture, this one here. So if I look at this picture here, you have the energy storage system with the container that we talked about a little bit earlier. And then there's cables that go underground from this container to the converter or the inverter.
Mm-hmm.
Those cables are underground. And then there's a jurisdiction issue as to whether or not the field evaluation or certification in some cases include those conductors or not. And I think that by the changes that were proposed in 6.1, that helps clear that up so that an energy storage system can just be the container with the batteries and the controls for the batteries, and not for somebody to say that, yeah, it has to include the inverter. And it separates those two issues and avoids the conflict of jurisdiction that way. Thank you.
Okay, thanks very much, Steve. So if I could just welcome back our other speakers to join myself and Steve on the stage, or metaphorical stage, I suppose. Yeah, we'll see if we can take on some of these tricky audience questions. And so where should we get started with? So Steve Matheson asked a question whether there's a distinction between a rack level and a container level when doing the testing. I don't know if this might be one for DMV, perhaps.
Yes, so there is the I guess differentiation comes in the definition of how you define the unit. So sometimes the unit is defined by that rack level. Sometimes it's defined as the entire enclosure. It just depends on really how you're doing the test and what you want to show with the test. We do recommend talking with whoever is running the tests very closely and working with them to look at the intention of what you're trying to get out of it. And then they can help you define what that unit is, whether it's the rack or the entire enclosure.
Okay, great to get that clarified. So I was just wondering, as I said, we did have a lot of questions about field versus factory acceptance testing. And I think Steve very articulately kind of addressed that from the standards perspective. But Larry, I'm just thinking, as someone as an integrator, major integrator, let's say, that is clearly, there's a couple of questions directed, I think, towards yourself and for IHI TerraSun on that. And I think there was one somewhere along the lines of, why do one and not the other, or something like that. I'm sorry, the exact wording escapes me, but could you just maybe give us a flavor of why each of those matter and kind of what the different steps and approaches are from the system integrator perspective, I guess, on a project level, perhaps?
Sure. What it comes down to is how often the product changes. So if you think about what UL's for in your home, if you have a toaster, you're going to make the same product over and over and over again. You certainly would do a factory UL listing on something like that. But in the energy storage sector, we see the battery products changing frequently as chemistry changes, as more efficiencies are found to get more energy density. And so because of that, to go through the factory listing on every time there was a new product, it would become very expensive. And in an industry where we're trying to make the best value for our customers and for really the consumers of electricity, it winds up being a more economical decision to do a field listing when you have a new product. And also then you do a listing on exactly what's there instead of trying to make a product that fits all needs. You can tailor that product how it's necessary in the field.
Okay, so there needs to be some project by project work really done, I guess, doesn't there?
Right.
At the end of the day, yeah, absolutely. And I think there was quite a few questions on particular safety features. So I don't know whether to ask these separately or together, but Tom Starr asked about addressing the use of gaseous suppression on the battery energy storage system level. And we also had okay, let's keep them separate. So yeah, we had various questions about the kind of gases and composition of gases and, detecting those, the standards regarding them. Mark, I think you kind of alluded to some of that in your piece. And I'm sorry that the question I'm asking isn't exactly what the audience member asked, and perhaps isn't exactly phrased as articulately as I could, but could you just offer us a few thoughts on that? And because I understand that the way kind of gas detection is treated in these standards is, again, is one of those big evolving pieces, I think.
Yeah, so at least for lithium-ion systems, so a lithium-ion system does not, under normal operating circumstances, generate flammable gas. Now, for NFP 855, there are provisions for systems like lead-acid batteries, where hydrogen gas is generated during normal operation, to have gas detection systems. So they aren't required for lithium-ion systems, but DNV does like to see gas detection systems within containers. And as was alluded to in the presentation, the way it's worded in NFPA 855, if you do choose to use a gas detection system, it needs to meet all the requirements of having emergency standby and backup for a designated period of time. So that's if it is installed in the system, it needs to meet those requirements. Okay.
And following on somewhat from that, we had a good few questions about the use of water as as part of fire suppression, and I think this is kind of alluding to what we've been hearing from the field, that there have been occasions where, let's say, sprinkler systems have kind of not worked exactly as might have been intended, created a short circuit, and it's kind of the battery cell that gets the bad rap and kind of seems a little bit unfair. But yeah, what are your views I guess on water-based suppression, and perhaps I guess after DMV could take a little crack at answering that. I don't know if Larry, you can maybe just give us a bit of an overview on IHI TerraSun's kind of overall perspective on some of the best kind of fire suppression methods. But sorry, Carrie and or Mark, I don't know if you could just kick us off with that one, please.
Sure, happy to. So there's definitely a lot of pros and cons when it comes to water for use in fire suppression systems. So one of the pros is that it's definitely the best on the market right now to cool those battery systems. So if thermal runaway does happen, there needs to be a way to cool those batteries to prevent the propagation of the thermal runaway to either the surrounding units or the surrounding batteries, depending on how the OEM wants to manage that. And while there are other things coming on the market, water is just right now tops everything. So some of the cons is that you're right, it does, if not done properly, or say there's water infiltration from some source, it can cause short circuits, which then can cause the thermal runaway, which can, make these batteries go on fire. So we have seen that, unfortunately, in the industry. The other cons is some environmental considerations. So if you have water runoff, how are you going to deal with that environmentally? So there's definite pros and cons. There's for your philosophies for fighting these fires, a lot of times the OEMs suggest that you cool the surrounding batteries. So if you're looking at a containerized solution, putting water on the containers, so hopefully the water will not infiltrate into those containers, but instead cool the surrounding enclosures to stop the propagation of that fire. And it's kind of assumed that if you're using water inside of an enclosure, you're just going to scrap that battery completely.
Sure.
Yeah.
Okay.
I also want to add that the effectiveness of a suppression system is really dictated a lot by the design. So maybe sprinklers on the roof of a container aren't the best location for them. We've seen a lot of different designs, a lot of innovative designs where suppression agents are delivered directly to cells within modules. And if you can get suppression agents to where the source of heat is, or where the failure is, it can be much more effective than kind of trying to blanket a container with, say, a sprinkler on the ceiling.
Okay, cool. And Larry, yeah, if I may, kind of what's your philosophy when it comes to engineering some of these projects in terms of that kind of not specifically water, but just generally kind of fire suppression, and putting those layers of protection in that systems need.
Right. We do see that, as said, water is the most prevalent use nowadays. Almost all of the new projects on these utility scale sites have requirements for on-site water storage tanks. So some form of source that is always filled, ready to go. But in many cases, it's there as a means to protect the surrounding area. So as kind of mentioned, there's risks when using water, and sometimes what that will do is prolong the fire. So the system, if it does get into thermal runaway, will burn. If you cool it, you'll just have it burn longer often, and it will require large amounts of water. And then, as mentioned, there could be potential environmental hazards that need to be considered. So a lot of that will come to the local authority and the town fire marshal for how they specifically want a fire managed. And then TerraSun, we work to provide an emergency response plan as a guideline to our customers that they can use for approval with those authorities.
Sure. I mean, I think it's really important to have that in place. I think, what we're hearing increasingly from the market is, of course, you have to design everything to be safe, but at the same time, if something, if you're a fire marshal and something's happening in your town, then you need to know what to do at, any given circumstance, I guess, so I think it's really important to hear that, I guess. Okay, folks, I think we've got time just for one more question online today, if we can. But at the same time, as I mentioned before, the speakers via IHI TerraSun will be, delighted to follow up with some of these really involved questions offline and carry on that discussion. With that in mind, I think there's one that is perhaps something for people that might be a little bit newer to the industry than perhaps some of you guys are, are used to talking with on a daily basis. But Gene Krasinski asked about, so the question is, please address NFPA 855 and its harmonizing with UL9540. So, I'm thinking for folks that are kind of getting to grips with the battery storage industry and maybe not so aware of, the role that NFPA 855 plays in informing a lot of the other standards around it, kind of thing. What, you guys are much better placed to kind of take this on than I am. But perhaps, I don't know, Steve, is that something you could maybe just begin a little bit of an explanation of? And if any of the other speakers want to jump in, then by all means, please do. Oh, sorry, I think you've got muted there somehow, Steve. Sorry.
Yeah, I have to apologize. I was reading through the questions and I didn't, and when that one started, I didn't think it was going to be directed to me and I didn't pay enough attention to it. I apologize for that.
Oh, I'm terribly sorry. Okay. Anyone else?
Yeah, I can take that. So,
Sure.
The UL9540 is definitely separate, but works with NFPA 855. So 855 is its own standalone standard that has to be followed. And then as a part of UL9540, one of the requirements for a 9540 listing is to be in compliance to 855. So that's where, to get the UL9540 sticker on your project that says, I am compliant to that listing, you have to show that you meet all of the requirements that are applicable from NFPA 70, the National Electric Code, from NFPA 855, which would include meeting compliance to NFPA 68 or NFPA 69, and then also International Fire Code and many other standards. So they go together, they are separate, and then to meet 9540, you have to be compliant to 855.
That's terrific. Thanks very much, Larry. I'll tell you what, Steve, to finish up with, seeing as how, you took the time to read through the questions, is there perhaps one you'd like to pick out and answer for us, or for the audience rather?
There was one question regarding, and I don't have the question up there right now, but it was regarding the difference between field evaluation and certification, as far as how you can accept a field evaluation that has not gone through quality control as part of the field certification. Mm-hmm. And I think the thing that we may want to think about is that the reason that you have the quality control as part of the certification process is because the manufacturer is being trusted to follow the program and to put the certification mark on with in accordance with the file, and it's only audited 4 times a year. So there needs to be something in place to verify that, yes, in fact, they're following the program and they've got a quality process in place to do that. Whereas a field evaluation, we look at every unit. So it's not a matter of, yeah, they did the last one okay and this one's labeled. We look at every single one of them. Every single one of them has a dielectric test, for example. Every model has a temperature test, this sort of thing. So it's quite a different process doing a field evaluation as opposed to a full certification. Thank you.
That's great. Thanks so much, Steve. Okay, everyone. As I said, lots we could continue talking about, but I think for today, we're going to have to call a time on it there. But above all, I'd like to thank all of the hundreds of you that took part in terms of being the audience for this webinar. Many of you whom asked questions as well of our speakers. And of course, I'd like to give a big warm thank you to Carrie and Mark from DMV, to Steve from QPS, and of course to Larry from IHI TerraSun. Just want to say that their details are on there for the screen now. They have been for a few minutes, obviously, as you would have noticed. So you're more than welcome to get in touch with them, carry on your conversations. Yeah, your questions will get answered in the fullness of time. And I just want to say, from my point of view, thanks to particularly all of you working in the clean energy industry, Thank you so much for the work that you do, and keep it all up, and let's hope for a great 2023. Thank you so much, and goodbye for now.